Welcome to this explanator. Okay, we have a genuinely mind-bending journey ahead of us today. We're going on a deep, math-driven dive into the Adelic Langlands framework. Now, if you've been following this space, you know this is a revolutionary theory. It literally bridges two completely incompatible universes, the totally discrete, subquantum arithmetic world and the smooth, continuous geometry of classical physics. Get ready, because we aren't just skimming the surface. We're going to unpack the actual equations that make this wild synthesis possible.
So let's just jump right in. The grand challenge we're tackling today is this. How in the world do we bridge discrete quantum data with continuous physical space? For decades, there's been this fundamental disconnect, right? On one hand, you have subquantum, hyper-discrete data streams. On the other, the smooth, continuous fields of classical relativity. It's kind of like trying to perfectly translate the cold, hard ones and zeros of computer code directly into the fluid mechanics of a rushing river. Doesn't seem possible, does it?
Well, here is our roadmap to figure it out. First, we'll look at the Adelic Langlands framework as a whole. Second, we dive into spectral projection. Third, J-theory optimization. Fourth, logos field theory. And finally, number 5, Adelic synthesis.
All right, starting with section 1, the Adelic Langlands framework. Let's look at the global picture. Think of this 4-tier structural hierarchy as our vertical map for the day. We are going to start at the very bottom tier. That's spectral projection theory, our foundational operator and filtering bedrock. From there, we'll ascend vertically, moving right through J-theory, which handles all our algebraic and geometric mechanics, and then up into logos field theory, where we get our physical field realization. And finally, the whole shebang culminates at the very top in the global Adelic Langlands program. Now, to really grasp what we're integrating here, we absolutely have to define the two disparate worlds we're trying to synthesize. On one side, you've got the non-Archimedean topology. This is discrete, totally disconnected, fractal, and governed by p-adic numbers. Imagine it as ultra-high-density, cold, crystalline, compressed data strings. Then, on the other side, we have the Archimedean topology. This is our familiar continuous, smooth, differentiable space over real and complex numbers. Basically unpacked, macroscopic geometric fluids. We are slamming these two together. Moving to section 2, spectral projection, also known as the subquantum filter. Okay, so spectral projection theory is basically our functional analytic bedrock. The mathematical goal of this tier is absolutely crucial. It takes these raw, infinite-dimensional operator spectra and coarse grains those totally wild data streams into finite, usable, structured representations. You can think of it sort of like downsampling a massive, uncompressed audio file into a sleek MP3 just so you can actually play it. Without this mathematical sieve, we would literally be overwhelmed by an infinite sea of data. And here is the math making it happen, the Legendre UDD filter. If you look at the spectral projection measure there, it acts on the unbounded Cones-Dirac operator, which is basically our raw quantum noise, and it applies a smooth cutoff function to isolate the stable data up to a very specific energy scale, lambda. It's taking incredibly volatile data and translating it into a tight algebraic profile we can actually work with. It's a real game changer. That brings us to section 3, J-theory, which is all about geometric optimization. So J-theory's primary job is optimization and metric synthesis. It takes all those filtered spectral traces we just calculated, and it transforms them into geometric functionals. At the same time, it manages their stability using geometric invariant theory. This right here, this is the exact moment where pure arithmetic starts to literally become geometry. And this beautiful bridge is established by the metric push forward. Check out the Grothendieck-Riemann-Roch push forward in the center of the equation. What this effectively does is take the limit of our spectral density, those raw Adelic data streams, and it pushes it down to create a structured metric template on the base manifold below. By evaluating the spectral measure on these localized curvature operators, J-theory smoothly translates raw data streams into finite-dimensional algebraic moduli. Now, once we have that metric, we feed it directly into the J-functional. You can think of this functional as a massive optimization engine. By maximizing it, we minimize the friction in the spectral density. And the stunning result? Classical geodesic paths. The exact smooth curves that we always associate with gravity and spacetime, they actually emerge as the direct mathematical shadow of non-commutative operator spectrums. It's mind-blowing when you really look at the math. On to section 4, logos field theory dynamics. Logos field theory steps in to manage the smooth transition between our discrete and continuous topologies. It essentially treats the Adel ring as the fundamental domain,
And what it does is define our physical laws as nothing more than the stable interference patterns of the underlying arithmetic data stream. Take a look at the Adelic state factorization tensor to really see how this dynamic operates. The global state configuration is represented as a restricted tensor product. It perfectly locks together the non-Archimedean array, those discrete, super-rigid p-adic data packets, with the Archimedean wave, which represents our continuous geometric fields. It's basically the ultimate mathematical handshake between two different dimensions of reality. Okay, almost at the top. Section 5, Adelic synthesis and global conservation. When we look at the local Langlands correspondence, it maps discrete, p-adic matrices straight over to continuous Hodge-Bile weights. But the real magic happens with the packing fraction phase diagram. As this ultra-dense, crystalline string data passes through the Adelic interface, specifically through the Mellin sieve, it actually decompresses. It literally fluidizes into continuous, macroscopic physical trajectories. You are watching data melt into physics. But of course, this raises a huge question. Does the math actually balance out? The insane architectural symmetry we've been building demands perfect conservation. So this framework isn't just some neat analytic trick. No, it is the fundamental thermodynamic conservation law of Logos field theory. And here is the mathematical mic drop, the global functional equation. Just look at how the automorphic L function perfectly balances against its dual representation. This single, elegant equation proves that the data decompressing from the discrete quantum core perfectly, exactly matches the geometric energy dissipating into our macro universe. The arithmetic strings and the continuous forces are perfectly conserved payloads. Let's quickly unpack these balance variables. The standard automorphic L function, L of S pi, acts as our global product integral. Then we have the global epsilon factor dictating critical phase shifts as data jumps across the topologies. The arithmetic conductor, Q to the S, rigidly fixes the continuous metric curvatures based on the data level. And finally, the dual representation ensures that every single bit of local finite data perfectly anchors at infinity. So through the exact rigorous mathematical flow of the Adelic Langlands framework, we've seen how continuous physical trajectories literally emerge directly from discrete arithmetic optimization. Which leaves us with this. If our physical reality is just a semi-classical shadow of these discrete arithmetic operations, are we actually living in a continuous universe? Or are we just experiencing an endlessly unwinding perfect data stream? Something to think about, right? Thank you so much for joining me for this explainer. And keep questioning the math behind our reality.